So welcome to the last lecture of the afternoon session today. Speaker is Antonio Lei from University of Laval, and he's going to talk about Euler systems and Beilinson-Flach elements. Over to you, Antonio.
Thank you for the introduction. I also want to add that I'm now also affiliated to University of Ottawa. It's a great pleasure to speak with you all on Zoom. I want to thank the organizers for come up with this really wonderful program. I'm sorry I can't be there in person. I hope I will have the chance to be there next time. So I want to talk about Euler systems and Beilinson-Flach elements. So I want to begin with cyclotomic units. So I guess when you look into the literature of Euler systems, quite often you will see, first of all, the definition, which is at first sight, maybe a little bit technical, and you might ask, why do we define these Euler systems in this way? And so I want to, first of all, illustrate things with cyclotomic units, which is always the first example people would give you. And so I want to tell you how we use cyclotomic units to prove results in Iwasawa theory before defining what an Euler system is. So once you've seen these elements in action, then hopefully when you see the definition of a formal Euler system, then it will make a little bit more sense why we define Euler systems this way. So, and I know that there are a lot of students in the audience, so I want to make the talks a bit light and not too technical. So I won't give you too much technical details. I would rather give you the general ideas of how things work and what we do in the in this area. So let's begin. So first section is about cyclotomic units. So some good references for cyclotomic units are, sorry, it's a bit early for me here. So, okay, so references, a really good reference would be the book of Coates and Sujata, which is called Cyclotomic Fields and Zeta Values. And this is the reference that I will follow really closely in this chapter. And other books that you might find useful is the book of Lang on cyclotomic fields. And also another classic on this area is the book by Washington called Introduction to Cyclotomic Fields. Okay, so let me begin by telling you some basic properties of cyclotomic units. So first of all, I want to fix a collection of primitive nth roots of unity. Zeta m, so m will run through all the integers that are at least 1, and I want to make sure that they're compatible. So when I look at the m times nth root of unity, when I raise this root to the nth power, I will get the mth roots of unity. So one easy example you can write down is simply taking e to the 2 pi I over m. So this is a primitive nth root of unity, and it is compatible in the sense that I just stated here. And so we would be interested in the cyclotomic extension, namely Q adjoint zeta m. And we know that the ring of integers of the cyclotomic extension is simply given by Z adjoint zeta m. And we will write E m for the group of units in this rank of integer. And so now we will write VM will be the multiplicative group inside this field generated by these roots of unity, so plus and minus zeta m, as well as 1 minus zeta m to the a, where a would be between 1 and n minus 1. And now the group of cyclotomic units in this field is given by, we will denote it by Cm, which is the set of units intersected with this group Vm. And so in general, you might want to talk about cyclotomic units in an abelian number field. So if K is an abelian number field, then we know that K is inside some cyclotomic extension. So this is this is Kronecker Weber. And then in this case, we just define the group of cyclotomic units in K to be CK, which is the unit of K of OK intersect with CM. Okay. So this is the definition of cyclotomic unit. So just to give an example, so we will be interested in, for example, the totally real field inside the cyclotomic extension. So let's say we look at Q zeta n plus, which is simply Q zeta n intersect with the real number, and this can be explicitly written as this. And so yeah, you have a total real field, and you can try to write down an element in this group like this. And like you can just do the calculation and realize that this is given by the sine function of pi a over n divided by sine pi over n. So yeah, you have an explicit element like this. So we will be interested in this field. So I'll write from now on, we will introduce this notation. So from now on, we write En plus to be the group of units in zeta p to the n plus. So what I mean by this is, so this is the range of integers of the totally real field given by the cyclotomic extension adjoining p to the n root of unity, and then I look at the group of units of this rank of integers, and then I'll write Vn plus to be V q zeta p to the n plus, and then I'll write Cn plus to be C q zeta p to the n plus. Okay, so right, so I will be interested in these. So I give you some results without any proof. So yeah, so here P is a fixed odd prime number. Some simple results that we can prove is that when you look at this Cn plus, so the cyclotomic units in this totally real field, it is generated by, you would have -1 and this explicit element, which I'll write CRA to be these elements. So we have here. Wait, sorry, I don't think I need this. This is not necessary. Sorry. Okay, so maybe I don't need this either. Okay. Yeah, sorry. Yeah, I should check that. Okay, so here I want A to run through the integers between 1 and 1/2 times p to the n, where A and p are co-prime. That's first thing. The second thing is that, okay, if you look at the cyclotomic units for the not the totally real field, but like the whole cyclotomic extension, then it is generated by the Cn plus and zeta p to the n. Okay, so this is the first thing you can try to prove. The second thing you can prove is that the index of the cyclotomic units inside all the units in the group is finite. So this is a finite subgroup, and it is equal to, the index is equal to the class number. Of my field. So I'm not gonna prove this, but I just want to give you a rough idea how to prove this theorem using this lemma. So the point is that what I want to tell you with this theorem is that the cyclotomic units defined like this give you some kind of arithmetic information about my field, namely the class number of this extension. So the idea is that we can apply the analytic class number formula. Which tells you that the class number is related to some zeta function. So so the formula says that when you look at the zeta function of an abelian number field of K, then you have something like this. So in the case when K is this totally real field Ku zeta p to the n, yeah, so since this is totally real, so you don't have the R2, you just have the R1. And so what you get is that the right-hand side becomes something like this, 2 to the d minus 1 times the class number times the regulator, and then divided by some product of Gaussian. So here, where this G is just the Galois group of K over Q, and D is the degree of my extension. Right, so you know that you can calculate the class number using this formula. And so you want to compare the group of cyclotomic units with the group of all the units in this field. So all the units in this field would give you this regulator term. So you try to work out the regulator you calculate using these cyclotomic units. And so if you do the calculation and just to work out what you would get using this cyclotomic units, maybe I shouldn't use tau, use sigma. Okay, so you look at all this, and then you can work out this determinant, and you would find that it gives you something like this. And so this is essentially this what you get on the other side in this formula. And so so what it tells you is that the group generated by the cyclotomic units should have a finite index in the group generated by all your units. And then
Can I ask a question?
Oh yeah, sure.
Why do Gauss sums appear on the right-hand side? I would think that everything except for HK and RK are explicitly understood.
Yeah, so I think yeah, so I guess I think there's some formula relating the discriminant to this Gauss sum. And the reason I want to have this Gauss sum, the reason why I want to express this in terms of the Gauss sum is because I want to compare this with this regulator that I'm calculating.
I see.
Yeah. So I think it's called discriminant conductor formula or something to go from this to this. Yeah. So okay. So now yeah. So now you compare the two sides, and then you realize that the group generated by this element should have a finite index, and the index is precisely given by the class number. So so this is kind of the idea. Yeah, so this is the first interesting property that I want to tell you about, is that these cyclotomic units encode some arithmetic information about my number field. So yeah, so then we can conclude using lemma 1.1, because these are precisely the elements generating my group of cyclotomic units. Okay, so the second thing I want to tell you about these cyclotomic units are the norm relations these elements satisfy. So the first thing I want to say is that, okay, let's say L is a prime and M is an integer which is greater than 1. So I have a norm map going from the extension given by M times L root of unity to the M cyclotomic extension. So I call this the norm map. Oh, sorry. Okay, and so this extension, when you go from the mth cyclotomic extension to the mth cyclotomic extension, the degree is either L or L minus 1, depending on whether L divides M or whether L does not divide M. Okay. And so you can then ask what is the minimal polynomial of zeta ml over q zeta m, and it is given by, you can just try to work it out, and it turns out to be x to the L minus zeta m if L divides m. If L does not divide m, is slightly more complicated. So clearly your zeta ML is still a root of this polynomial, but one of the roots will be, in fact, already in the ground field, namely x minus zeta m to the a, where a is an element in Z such that a times L is 1 mod m, right? So yeah, yeah, this is also, yeah, when you put this inside this polynomial, right? The fact that a times L is 1 mod m would tell me that this element raised to the Lth power would give me zeta m. And this element is already inside this extension, right? So, so this shouldn't be in the minimal polynomial. So this is why when L does not divide m, the degree is only L minus 1 rather than L, whereas if L divides m, then you can show that actually every root of this polynomial is not in Q zeta m. And so, so you have these two cases to consider, okay? And so once you know that the minimal polynomials, the minimum polynomial of zeta ml is given by this, then you can work out what you get when you look at the norm of this element, and it would simply be 1 minus zeta m if L divides m, whereas if L does not divide m, then it would be given by the same element, except that you have to, like this extra factor here would tell you that you have to modify it by this zeta L minus 1. So like L minus, why do you have minus 1? Because, well, this A is like the L inverse mod m, right? And so this is a sigma L is an element in my Galois group sending zeta m to zeta m to the L. Okay, so you see that the norm of these elements is slightly different according to whether L divides m or not. And so, like, when you try to work out what happens to these cyclotomic units, then you can find that maybe maybe that's not a very good notation. Okay, so using this, we can show that if A is co-prime to 2ml, then we can work out that this is given by something like this. Sorry, I'm not writing this really well. So I guess earlier I should have write this should be 1 minus A over 2, sorry. Yeah, this should be this. Okay, so yeah, this will give me this generator. When I just norm this generator over ML, I get this generator over M. Whereas if I look at the case where L does not divide M, I would get the same thing, but again, I would have to add this factor 1 minus sigma L minus 1 in the image of the norm of this generator. So somehow, what I want you to remember from this is that the cyclotomic unit satisfied some kind of norm-compatibility relation. So when you go from a cyclotomic unit over the ML cyclotomic field to the mth cyclotomic field, you will send a generator to another generator, except that depending on whether L already divides M, your norm relation would be slightly different. Either you just get another generator or you get a generator modified by this factor. And this will be useful for us later. So for the time being, I just want you to remember there is such a relation. Okay. Right. So now I have told you what cyclotomic units are, what sort of arithmetic information it encodes, and some kind of non-relation they satisfy. The second thing I want to tell you is how these cyclotomic units are used in the study of Iwasawa theory. So now I want to say something about Iwasawa main conjecture. So again, P will still be a fixed prime odd prime number. So P is odd prime, and I will be yes.
Hello. Yeah.
Yes.
So in the norm of that element, the second one, when L does not divides M, so the power 1 minus sigma A inverse. So one is identity.
Sigma L minus 1. Yeah.
Yeah. So one is identity map on that.
Exactly.
That is,
yeah.
Okay. Okay. Thanks.
Yeah. So like you would what it means is that you look at this. So when I say 1 minus sigma L, what I mean is like this element divided by this element applied to sigma L minus 1.
Oh yes. Okay.
Yeah, that's what I meant. Yeah. Yeah. This is why do I have this extra factor is because of this denominator here. Like this A is like an L inverse, because A is the L minus 1 mod M, and so this is why I have a sigma L minus 1 here.
Yeah, thanks.
Is that okay? Yeah.
Yes.
And when we look at that norm for the first case, shouldn't it be 1 minus zeta M to the A, not to the L?
Oh yeah, that's correct. Yeah, sorry about that. Yeah, thank you. Okay, right. So now, yeah, P will be an odd prime. I will look at this totally real field that I have mentioned earlier, and I will write Gn for the Galois group of this extension. And I am interested in the union of all these extensions. So for those of you who are not familiar with Iwasawa theory, this is what we do in Iwasawa theory. We want to look at a tower of extension and try to understand arithmetic behavior as you go up the tower. Okay, and so I will write G for the Galois group of F infinity over Q, and this Galois group will be isomorphic to this is finite group of order P minus 1 over 2, and this is cyclic. Okay, and then I will write U and 1 to be the set of local units of my of QP adjoint zeta P to the N plus, and I want to this one means I'm looking at the units that are congruent to 1 modulo the maximal ideal. And then I want to look at EN1 to be the completion of the global units intersect with these local units that are 1 modulo the maximal ideal, and then CN1 will be the completion of similarly, we will be looking at those cyclotomic units intersect with this UN1. And then we would be looking at the inverse limit of these units. So, all right, sorry. So U infinity 1 will be the inverse limit of the local units. E infinity 1 will be the inverse limit of the global units. And C infinity 1 will be the inverse limit of the cyclotomic units. And the connecting maps are just non-maps. Another important thing we will need is the Iwasawa algebra, which I will denote by lambda. And often we write it as ZP double bracket G, and this is simply the inverse limit of these group rings of Gn. And so this as a ring is isomorphic to this ring of power series in X. So this is power series in X with coefficients in this group ring ZP delta, and X can be identified with a topological generator -1 or right. So remember, G here is this product. We have a finite group and a ZP, and so when you look at this Iwasawa algebra, you would have this delta coming in as some coefficients, and then once you fix the generator for the ZP plot, then you can identify all the elements in here as some power series over X, and where X can be identified with gamma -1. Okay, and right. So now what I want to say is that, okay, once you've defined these objects, and these inverse limits, they are all lambda modules. And so now you want to study the structure. Oops, sorry. You want to study the structure of these modules over lambda. So one thing I want to tell you is that the cyclotomic units has simple structure as lambda module. It is just generated by one single element. So here B will be a system of elements, which I'll write as Bn, where Bn is given by this explicit cyclotomic unit. Times some unit, so where A is a integer coprime to P and U is some p-adic unit, and it is actually is the P -1 root of unity, such that U times A is 1 mod P. So yeah, so what I want to say is that this is actually a very explicit generator. So the cyclotomic units, you kind of understand quite well what it looks like, because remember earlier in I think lemma 1.1, I told you how to generate the group of cyclotomic units. So you can really write down those elements explicitly. So when you look at this inverse limit, you can also write down an explicit generator in this way. So the other groups maybe not as explicit. So, but what I want to tell you is that we can use the cyclotomic units to study certain Galois modules, Galois groups, in fact. So I'll tell you what these Galois groups are. So
sorry, so in the denominator of Bn,
yeah.
there is,
I'm sorry?
denominator of Bn, there is an inverse missing.
Bn.
In the
Oh,
denominator.
I see. Oh, yeah, of course. Yeah, sorry. Yeah, of course. Yeah. Yeah, of course. Otherwise, yeah, that's not a very nice element. Sorry about that. Okay, so right now, tell you what groups we want to study. So Mn will be the maximal 8 billion p extension of Fn that is unramified outside P. Ln is the Hilbert, well, the P part of, well, maybe I'll say it like that, is the maximal 8 billion P extension of Fn that is unramified everywhere. So this is essentially the P part of the Hilbert class field. Oh. Okay. Right, and then I'll look at the union of this field. Right, so you have this diagram. So you have M infinity, L infinity, F infinity, and I will call this X. The Galois group of this extension is X infinity, and the Galois group of this extension is called Y infinity. Okay, so right, Y infinity is telling me about information of the Hilbert class field. So I'm looking at the unions of these Hilbert class fields. So the Hilbert class fields, remember, is given by the class group, right? So the Galois group of this extension will give you the class group. So remember, in theorem 1.2, we know that the quotient of E1 infinity over, so maybe I'll say this, like the global unit quotient by the cyclotomic unit is related to the P, it will be related to the P part of the class number. So I mean, yeah, that's precisely tell you what this Galois group Ln over Fn is. So there's a link between the quotient of the global units by the cyclotomic unit and this Galois group. So now we are looking at the union of all these L infinity. So it suggests to us you would expect a link between Y infinity and this E1 infinity over C1 infinity. So in some way, what you're trying to do is to hope that you can package this link, which is a priori a link at the finite levels of your tower of extension, to a link over the whole tower. Okay? And this is what Iwasawa theory will tell you. And so in order to study this link more precisely, I told you that these are lambda modules. So in fact, Y infinity and X infinity are also lambda modules. It is just because, remember, lambda is given by the Iwasawa algebra of G, where G is the Galois group of F infinity over Q. So you can find a conjugation of, like, the gamma would act on this group by conjugation, essentially. So this is, yeah, so the Iwasawa conjecture will tell you that So there should be a link between y infinity and E as lambda modules. Okay. So I'll explain this with the okay, yeah. So what should I do? Yeah, okay. So I'll try to make this a little bit more precise for you. So before I do that, I will just tell you that yeah. So there's a okay. So how do we study this? So it's the way we do this is that there is an exact sequence of lambda G modules, well, just lambda of sequence of lambda modules, which looks like this. So you have right. So yeah, so we want to link this module to this module, and so it turns out that in order to study the link between these two modules, you can study the link between these two modules as well. So this turns out to be equivalent. So let me explain a little bit more how we do this. So in order to explain this, I want to tell you another result, which says that there's a lambda morphism, which I will write as L1, which goes from the local unit to lambda, just lambda. And so this is called the Kalman map. So it allows you to convert non-compatible local units to elements in the Iwasawa algebra. And it turns out that when you apply this to these cyclotomic units, you would get the following. Where IG is some augmentation ideal and zeta p is the Kubota-Leopold periodic function. Okay, so this is another interesting thing that about cyclotomic units is that you can recover the Kubota-Leopold periodic function via this Kalman map. So what this tells me is that when I look at this term is given by, well, this is isomorphic to this quotient. Okay, so in particular, is a torsion lambda module. Yeah, I keep writing lambda G, but lambda G is lambda. So yeah, okay. So this term in the middle, we have a very explicit description in terms of this analytic object, this term we also have some extra information. Is that the y infinity satisfies a control theorem, meaning that when you look at the gamma and co-invariant, you will recover what happens downstairs. Okay, so using this, it would tell you that, so because this is a finite group, right? So the fact that when you take gamma and invariant, you get a finite group, meaning that y infinity is not very big as a lambda G module, neither. So it would tell you that this is also torsion lambda module. And so now you know that this is a torsion lambda module, this is a torsion lambda module. So just by looking at this exact sequence, you deduce that this is also torsion and this is also torsion. So everything is torsion in this exact sequence. And there is a structure theorem about this kind of modules. So I'll tell you what it says. So if M is a finitely generated torsion lambda module, then
sorry, the augmentation comes in because of some pole.
Exactly. Yeah. Precisely. Yeah. The Kubernetes-Leopold function has a pole, and so it doesn't live in lambda. So that when you multiply it by the augmentation ID, it would cancel out the pole. Yeah.
Thank you.
Yeah. Thanks. Okay. So right. So the structure theorem says that if you have a finitely generated torsion lambda module, then you have elements in lambda and a finite lambda. Well, maybe I'll just say a lambda module Q with finite cardinality. Such that you have the following exact sequence. So you would have a direct sum of quotient lambda modules given by these elements. And then you would have your original module in the middle, and then you have the module of finite cardinality in the end. So what it tells you is that this module is not very far from a direct sum of quotient modules. So it's a bit like modules over DIP. If you have a torsion module over DIP, you know that it will be a direct sum of cyclic modules of this one. But here, lambda is not a DIP, and so it doesn't work. But then up to some finite co-kernel, you will have this morphism. This is a lambda. This is an exact sequence of lambda modules, and then we define the characteristic ideal. Characteristic ideal of M to be the ideal generated by these products of elements. So we multiply all these elements together to give you an ideal in lambda. And it turns out that this is a well-defined object. And yeah, this Fi have some uniqueness about them. And so essentially, when you define the characteristic ideal of a torsion lambda module, it kind of tells you how big it is as a module. It's a bit like its cardinality, like up to this finite thing, right? And so, yeah, the Iwasawa conjecture will. I'm sorry.
Excuse me. Does it behave a lot like the fitting ideal, which came up in another lecture in this meeting?
Right. Yeah, it is indeed related to the fitting ideal, except that we are getting much less information than the fitting ideal here. Like the fitting ideal will be, it's not necessarily principled, like because you have this determinant and you have a like you have to look at the generators and relation. So here, this is a much coarser object. It's not giving you everything about the fitting ideal, but there, if I know the fitting ideal, I think you can recover the characteristic ideal. Another thing is that here I have to assume my module to be torsion. I think when you define a fitting ideal, it doesn't have to be torsion. So there are some slight differences between the two objects, but they are definitely behave in a similar manner.
I see. Thank you.
Yeah. Okay. So right. So you have this characteristic ideal, and remember in my exact sequence, all these objects are finally generated torsion lambda module. So for each of them, you do have a characteristic ideal. So the Iwasawa main conjecture says the following. It says that the characteristic ideal of E1 infinity over C1 infinity should be the same as the one for Y infinity. So this is what I was trying to alert to earlier, is that there should be a link between this module and this module in some way, just by looking at what happens over the finite level. So somehow you can package all this information over finite levels together to give this statement. And another thing you can observe is that this is equivalent to the characteristic ideal of X infinity should be the same as the term in the middle, which was U1 infinity over C1 infinity, and we know what it is precisely. It is given by the ideal generated by IG times zeta P, right? So here, remember, U1 infinity over C1 infinity is isomorphic to this quotient. So this is a cyclic module, so you know precisely what the cyclotomic, what the characteristic ideal should be, and it is given by this ideal. So the Kuberto-Leopold PLL function, which is a very analytic object, should be related to this algebraic object. So remember, X infinity is some Galois group of my extension over F infinity. So a priori, this is a very algebraic object. So the main conjecture relates somehow the two worlds together to study what links you should get between them. Yeah. So right. So what I want to explain to you now is that how we can prove this main conjecture. Again, I'm not giving you all the details because I won't have enough time, but I want to give you like the main ideas behind the proof. So in fact, I will only prove, so the goal is to explain how to prove this divisibility. And then you will see some of the properties I explained to you will be useful for this proof. Okay, so yeah, I think I have 7 minutes, so I won't be able to finish what I want to say probably, but I'll just set things up and then I'll continue in tomorrow's talk. Okay, so remember, yeah, we have this Y infinity. So Y infinity is a torsion lambda module. So it sits inside an exact sequence like this, where Q is a finite module. And another thing I'm not proving is that this quotient of global unit by the cyclotomic unit, it turns out to be very simple. So it is a cyclic lambda module. So remember, I told you that C1 infinity is generated by one single element. So we know this module pretty well. And this E1 infinity is not too bad either. And in fact, yeah, you can show that by some control theorem again, by going from your whole tower to finite level, you can try to understand the structure of this quotient, and it turns out to be a cyclic module. So the goal is to, so we want to prove that this product of Fi should divide this beta. Okay. And to prove this, we will project things to finite levels. So these are objects over the whole tower, and we will try to prove this divisibility by projecting things to finite levels. I will call this F. Yeah, FM, I think, yes. Yeah, okay, FM. Okay, so okay, and then I'll introduce a few more notation. We'll let A to be the Galois group of LM over FM. So this will be related to Y infinity gamma M quotient. So this is gamma M co-invariant. So this is by the control theorem. So right. So we have this, and then I will write pi to be the Galois group over F, the Galois group of F over Q. So this would correspond to projecting lambda to this finite level, and then correspondingly, I have this group ring for this Galois group, which I will denote by R. And so, and then I will have, I write PR for the projection from lambda G to this R. Yeah, so instead of looking at things over lambda, then we would be looking at lambda over, R over the projection of beta, and it would be a finite quotient. And then also we have this Q, which is a finite lambda module, and we will fix delta, which is an alienator of Q. And then, yeah, try to, yeah, I'm not sure whether I have enough time to say everything. Okay, so fix S to be a power of P that alienates these two quotients. And then, okay, so these are just kind of technical. So, yeah, and then I'll write T to be this P power, which is a P power that is greater than or equal to P to the M. And then I will try to do things modulo T. So we already project things from the whole tower to finite layers, and I will try to project things to modulo T. Meaning, so I will write R, curly R to be this group ring over Z mod T, and then we will prove the divisibility over R, and so and then here and then let M goes to infinity. So once you let M goes to infinity, right, the pi would become closer and closer to my G, and Z mod T will become closer and closer to my ZP. So this is how the proof that I want to present to you go. So yeah, I think I'm running out of time, so I'll stop here. Yeah, I'll continue tomorrow, and I'll try to explain how the proof goes tomorrow.
So let's thank Antonio for his talk.